Hi everyone, welcome to Algebra 1, Lesson 10-2, the cube root function. In this lesson, you'll be able to identify the key features of the cube root function. And the lesson vocabulary would be the cube root function. So let's look at critique and explain. Emilia wrote several radical expressions on the whiteboard. We have roots over here, right? We have the square roots and the cube roots. Let's evaluate each expression and explain how to plot each value on a real number line. So can we evaluate each one? So square root 49, this is a perfect square. This is equal to 7. Square root 27 is not a perfect square. But cube root 27 is 3 times 3 times 3 would be 27, right? 3 cube. So then the root is 3. And then cube root of 72 would not be a perfect cube, right? So these ones we have decimals, right? If it's not a perfect cube. This one is undefined, and then because it's negative, there is no way there's a root that will be multiplied twice by itself to get a negative number, because everything multiplied twice is positive. Cube root of 3, this is also not a perfect cube. This one, 2 times 2 times 2 is 8. So 16 is a perfect square, but not a perfect cube. So this one is also a decimal. So yeah, so how could we plot each value on a real number line? So in pre-algebra, we learned how to estimate these roots using the square roots, the perfect cubes, and the perfect squares. So here, this one, we're going to compare the perfect squares. So 27 is between which two perfect squares? 16 and so 27 is between 16 and 25. Wait, no, not 16. 25. 25 and then 36, right? So that means square root 27 is less than root 27 is less than root 36, right? So root 27 is somewhere between 5 and 6. Square root 25 is 5, square root 36 is 6. So it's going to be between 5 and 6, right? So it's going to be 5 point something. And then cube root 72, we can also use the same method where we compare the closest perfect cubes. So think about the perfect cubes. 2 cube is 2 times 2 times 2, 8. 3 cube, 27. 4 cube, 64. 5 cube, 125, right? So 72, cube root of 72 is between 4 and 5. So this is going to be about 4 point something, and it's closer to 4. So it's probably going to be less than 4.5, right? So you'll see which whole numbers it's closer to, and you can guess. And then root 2 is between the perfect squares of 1 and 4, right? So it's closer to 1, so it's going to be about 1.234, right? Probably closer to 1, yeah. And then this one, cube root of 3 is between 1 and 8, and it's closer to 1 than it's 8. It's to 8, so it's closer to 1. So this is going to be about 1 point something and closer to 1. And so cube root of 3 and root 2 are very similar. So this one you have to go specifically. And you actually have to guess and check the squares and everything. So yeah, so 1.1 square, you have to calculate it. 1.1, 1.21, so it's going to be 1.21, right? Yeah, and then you see which one it's closer to. Yeah. And then cube root of -16. This one could be negative, right? But it's still not a perfect cube, so it's between 1 and 8. So it could be between negative, no, it's going to be between -8 and -27, right? So this is going to be something between -2 and -3, and it's closer to where 16 is closer to 8, right, than it is to 27. So it's closer to 2, so 2.3, 2.4, I guess. Negative 2. It's closer to 2. Yeah, so it's about -2 point something. Okay, so you can plot each value on a real number line, just like that. You plot 7. This one is actually, if you simplify, it's 3 root 3. That's between 5 and 6, just like we talked about. Yeah, so let's organize it and write it one by one. So the first one is 7. Plot at 7. The second one is square root 3. So plot between 5 and 6. Then the next one is 3. Plot at 3 because we know it's exactly 3. And then the third one, if we simplify this, we can factor it out, right? So 72, factor out, we have 36, and then we factor out by 2 again. We have 18, 9, 3. So we can pull out the 2, and this is really 2 cube root of 9, right? So yeah, 9 is not factorable. It's yeah, this is not a square root, so you cannot take it out of the radical. So again, so this one is 2 and cube root of 9. So plot between 4 and 5. And then the next one, square root 2, which is between 1 and 2. And then the next one, undefined, or you can say it's a non-real value, so you can't plot it. Yeah, cannot be plotted. Can you see my font if I make it this small? Okay, and not be plotted. And then the next one is, it's just that if you simplify, it's just gonna be cube root of 3, and you can plot between 1 and 2. And the next one, it should be -2 cube root of 2. And you can plot between -3 and -2. Okay, so now part B, explain how evaluating a cube root function is different from evaluating a square root function. So obviously, cube root functions can be evaluated for all real numbers because it's possible that you can have a negative as a radicand, right? And then But the square root functions can only be positive, right? And real numbers and 0. So that's the difference. That's the major big difference. So cube roots can be evaluated for all real numbers, whereas square roots can only be evaluated for positive real numbers and 0. Okay, and then part C, Amelia states that it is not possible to plot either square root of negative 16 or cube root of negative 16 on the real number line. Do you agree? Partially, yes, right? Why? Which one is correct? Which one is not correct? So we wouldn't agree because the square root of a negative number will always be a non-real value. So yes, we can't plot this, but the cube root function here is defined for all real numbers. So even if it's a negative, you can still have negative negative number as your simplified decimal, right? So it could be something between -3 and -2. So this is possible. It's a real number. So no, we wouldn't agree because, whoops, I wanna make it bigger. The square root of a negative number will always be a non-real value. So square root of -16 cannot be plotted on the real number line, but the cube root function is defined for all real numbers. So the cube root of -16 can be plotted between -3 and -2. Okay, good. So we have critiqued and explained our numbers here using cube root and square roots. So the lesson essential question is, what are the key features of the cube root function? So we will look more into the cube root function. We've looked at the differences between the square root and the cube root, right? And now let's look at the overall function. So example 1, key features of the cube root function. What are the key features of f of x equals cube root of x? So this is the parent function, right? So the function cube root of x is the cube root function, obviously. So first we want to see the graph so that we can see the characteristics. So make a table of values, right? You can plug in all the domains one by one. When x is -8, you'll get -2 as an output. Input -1, output -1, input 0, output 0. So you can make a table of values for each one, plugging in points, right? Plugging in the numbers. And then you can plot the points on the graph, and you know this is going to be a curve because you see dots that are uneven, that have uneven slopes, right? So then it's gonna increase slowly over here and it's gonna decrease slowly over here. Your cube root function looks like this. So it's very similar to it's very similar to the cube function, except it's also it's also instead of going this way vertically, you have a horizontal cube function, right? This is how cube function looks like if you didn't know. You know how the square function looks like this and then the square root function looks like this? So it's like the half part of the square function because the square function cannot have negatives for the radicand, it only has positives, right? But the cube root function have all real zeros, all real numbers, right? So then it's basically your cube function just in a horizontal and then reflected, right? In a you just like rotate it and then flip it like horizontally, so reflected, and then it's the cube root function. All right, so as the value of x increases, so does the cube root. And yeah, so from left to right, it is always increasing. It is always going up. However, the rate of increase is going to be different, right? Yeah, so domain and range would be all real numbers for both. And the maximum and minimum values are really infinite, but you can look at the maximum and minimum values for intervals, specific intervals. So what are the maximum and minimum values for the interval -8 to 8? So obviously the negative part, right, would be the minimum value because the graph is increasing overall. So the further on the left side would be the smaller value for the function. So you want to figure out the value for -8. And so you plug it in, f of -8 is equal to cube root of -8, which is -2. So this is your minimum value, -2. And then the maximum value, using the same thing, you plug it in here. Cube root of 8 is 2, so +2 would be your maximum number. Okay, so if you have an interval, then yes, you can figure out the minimum and maximum. If you don't have an interval, it's increasing forever and and over here you have a arrow going down forever. So then it's there, you can't find a minimum or maximum. Okay, let's look at try number 1. What are the maximum and minimum values for the function of cube root of x over the interval -27 to +27? So using the same method here, figure out the endpoints and you'll be able to figure it out. Pause the video, come back when you are ready for answers. Okay, are you ready? So if you plug in -27, cube root of -27 would be -3. And then if you plug in +27, then it's going to be +3. So then the minimum is -3. And then the maximum is +3, right? Okay, let's look at example 2, translations of the cube root function. How does a graph of g of x equals cube root of x plus 4 compare to the graph of f of x equals cube root of x? So first, we can graph the function. This is the parent function, right? We have the inflection point, like the point at the origin, right? And then the curve goes backwards. So that's called the inflection point. And this point moves up 1, 2, 3, 4 units up. And then if you look at all the other points also move up exactly 4 units up. So then we see that this is a translation 4 units to vertically up, right? So shifted up to 4 units. How does this graph compare to this graph? So then this is still the parent function. It looks like we stretched it because the graph is shown more, extended more over here horizontally, but it's the same graph as this graph. It's just cut here, but if you continue, it's gonna look like that. And so that's the parent function. If you look at g of x, you'll see, compare your inflection point. That's the easiest point you can compare. It goes left 3 times and check if other points also do the same. So a comma 2 would be another one. 1, 2, 3. Yeah, it looks like all the points are going to go left by 3 units. So yes, it shifted left 3 units. So let's see if you can try number 2, a and b. Compare the graph of each function to the graph of f of x equals cube root of x. Pause the video, come back when you're ready for answers. Okay, are you ready? So part A, if you look at the equation, you can easily tell later by identifying h and the value of h and k. But here, you can also graph it, right, one by one, or you can compare the points, right? In your parent function, your original points are 0, 0, and then 2, 8, negative 2, 8. Compare these points, right? For the new function, you have 0, negative 2. And then you have 2, cube root of 2. Wait, a, 2, right? So sorry. Negative 2. Gotta switch that. So then this is 8. You plug in 8. So 8, cube root of 8 is 2. 2 minus 2 is 0. So 8, 0. Then you have negative 8. Negative 2 minus 2 is negative 4. So then compare these points, right? It all shifted down by 2 units. So this is shifted down 2 units. If it goes left and right, it's kind of hard to tell by comparing these points, right? Yeah, if you have uneven units that are seemingly going down, then maybe it's going left. So you need to check the other points too. So this is why graph is very, very useful. It might be very useful. So look at this one. The original points are this for the parent function, but for the new function, if you plug it in, you have 0, and then you have plus 1. Oh, okay. So 0, cube root of 1, which is 1. And then a, cube root of 9. So that's just cube root of 9, right? And then negative 8, and then you have cube root of negative 8. Yeah, and then, yeah, you might not know how to find the whole numbers, but try to find the cube root, like the perfect cube, right? So the perfect cube would be 8 here. So in order to make this 8, this radical 8, you want to add 7, right? So then you have a point 7, 8, and then you have to solve this. Cube root of 8 would be 2. Right, and then you have negative 7, negative 2. So then what you notice is that your x values have moved a little bit for the same y values, right? For the same y values, if it's negative 1, then it's 0, right? So 0, negative 2, and 2 for the y values. They're the same when the x values are subtracted by 1. So then now you know it's shifted left 1 unit. So you can either graph and compare, or you can look at the points and then just compare the numbers. But yeah, if you have the points, might as well graph the points and visually see it if you are not sure how to look at it just by points.